So this is one of our invited presentations from Max Millar-Blanchaer, currently at Caltech, but transitioning later this fall to UCSB. And he's going to be telling us about characterizing exoplanet systems in polarized light.
Cool. Can you guys see my screen?
Looks good.
Good.
Sorry?
It looks good.
Okay, great. Cool. So thanks so much for having me and inviting me to give a talk today. As Paul mentioned, I'm going to talk to you about how we can use polarized light to characterize extrasolar planetary systems. And so to give a little context, I'm coming at this from the angle of direct imaging. That's my background. And so here I have an image of beta pic B and an image over here of kind of one of the things we'd like to do with polarized light is understand the cloud morphologies by backing out measurements of polarized light. So in that context, I'm not going to talk about unresolved polarimetry of planets, which is also a very interesting topic, but not really what I'm going to cover today. The two things I am going to talk about today are characterizing circumstellar disks, as well as I mentioned, atmospheric characterization. And this is both in the near infrared using polarized light. So I think it's perhaps timely just to remind everyone of what polarization has done for us in our understanding of Venus. So this is kind of the classic example of how we've used polarimetry in the solar system to understand planetary atmospheres. And so back in the 70s, it was using the polarization phase function, so measuring the fractional polarization here as a function of phase angle, so the angle between the sun, the planet, and our observatory, to get this unique signature that was able to tell us that we're looking at about micron-sized particles of sulfuric acid clouds. And it was only using these polarization measurements that we were able to understand what these clouds were made out of. Now, moving back a little bit and thinking about how do we get polarization. So I'm gonna give you an example here, thinking about a circumstellar disk. So here we have a debris disk, a ring, that's seen not quite edge on, and we have our star here, and we're going to consider a dust particle out here at the ring ansi. And actually, instead of a dust particle, we're going to go a little bit more extreme and think about what happens as starlight comes incident on just an electron. And so in this case, we get Thomson scattering, and so we see we'll call it X and Y polarization incident on the electron. But for the observer over here, only one of those two polarization states can be transmitted. And this is because we know from Maxwell's equations that the polarization along the line of sight cannot be transmitted. And so through this scattering mechanism, we get this preferred linear polarization. And so the real takeaway here is that it's the act of scattering that gives us this polarization. And so in the case of dust grains, it's not a pure electron that we're seeing. And so the amount of polarization that we get may not be pure linear polarization. And also the amount of polarization that we get depends on the angle of scattering between the incident light, the scatterer, and the observer. And so we can take advantage of this fact in debris disks in high contrast imaging because we can look at just the polarized light rather than the total intensity. So here I'm showing you an image of the debris disk HR 4796A as seen with the Gemini Planet Imager. And here you can see if we look at total intensity, this is what we're always measuring with our detectors. You can see a hint of the ring in the background there, but it's covered in all this gunk, and this is residual stellar speckles that have been left uncorrected by the adaptive optics and coronagraph system. Instead, if we look just in polarized light, you can see the ring very clearly with no junk in the middle. So polarization, this is a technique called differential polarimetry, or polarimetric differential imaging, that allows us to just look for the polarized emission right next to a very bright source. And the other thing that this does is you can see if you look at the total intensity, you see that the ring actually kind of goes all the way around, but in the polarized intensity, you only see one side of the ring. And that has to do with the scattering angles and the scattering phase function of the dust within these, within the debris disk. And so here you can see just a schematic of the scattering angles that we have access to in this case, moving from 15 degrees at the front side here over to 90. And then at the back side, we get 165 degrees. And then you can start to look at different grain models. And so this is keeping the an example of keeping the composition of the grain fixed, but changing the grain size. And you can see the total intensity scattering phase function in black and the polarized fraction scattering phase function. So this would be the polarized intensity divided by the total intensity. And so you can see that both the total intensity and polarization fraction scattering phase function changes as we increase the grain size. But here, between this 1 and 5 micron case, the total intensity scattering phase function actually looks quite similar, but it's the polarization scattering phase function that really gives us the diagnostic power here. And so we can use this polarized light not only to help detect these disks, but to help understand what the disks are made out of. And so this has been applied recently in the GPI Exoplanet Survey Debris Disk Campaign. And so this was a subset of the GPI Exoplanet Survey, a subset of the targets where we looked at a range of disks that had either been previously resolved or had known infrared excess. And you can see a real range of different morphologies. We can see some very edge-on disks like this. We can see some very face-on disks. We can see some smaller disks, and we can see some bigger disks. And so all the images I'm showing you here are in polarized light. And so it's really taking advantage of this polarimetric differential imaging mode. I just want to give a big shout out to the GPI's team. It was a huge collaboration with many people involved. This is a photo back from a team meeting at UC San Diego. And I've highlighted in yellow here a lot of the people who have been working on the debris disk side of things. Getting back to talking about this enhanced detection ability of debris disks, I'm showing a few examples here of nearly face-on debris disks, maybe not quite face-on, but in the 45-degree inclination range. And these are all disks that we were only able to detect in polarized intensity. So it was only thanks to this polarization mode that we were able to detect these disks. And here on the right-hand side, you can see this is some of the results from the survey in a paper that came out this year by Tom Esposito, where you can see our detections are shown as triangles in an inclination versus LIR over L star plot. So this is the disk thermal brightness. And so you can see there's a cutoff where we only really detected things above 10 to the minus 4. But really here, I'm here to highlight right now the power of this polarization mode to push the inclination range of the disks that we can see down. And so this is a real strength of the polarimetry mode. Now, once we have these images of disks, one of the things that we can do with this is we can search for signs of hidden perturbers. So these are hidden planets that are having a dynamical effect on the morphology of the disk. And so two of the studies that I carried out, I'm going to highlight here. One is on the Beta Pictoris system, and one is on HD 157587. And here in this Beta Pic image, what we're seeing here is the Beta Pic disk as this kind of nebulosity. And I've overlaid the planet in total intensity and the disk we're seeing in polarized intensity. And so by modeling the shape of this disk, so this is just the disk is very forward scattering, so we're seeing it edge on and seeing very forward scattered light, so that's why the intensity is peaking at the center here. And by modeling the disk, we think that there's signs here just from the disk morphology that there's another planet that could be sculpting the disk at these very small inner working angles. And so we found the inner radius of the disk, the line of sight inclination, as well as the fluffiness can't be explained by beta pic B alone. And so since we wrote that paper, there has been a discovery of beta pic C via radial velocity measurements. But I can't say for certain whether or not that could explain these morphological features, because the dynamical scenarios that we explored in this paper were looking at planets outside of beta pic B and how that would affect the disk morphology. Whereas beta pic C has been discovered to be inside the semi-major axis of beta pic B. But I think there's some interesting work to explore those scenarios still out there. Now, in the case of 157587, one thing that we found in modeling this disk is that the disk is actually not centered. The center of the disk is not where the star is. It's slightly offset. And one way you can kind of see this is if you look down at this corner of the disk, you can see it kind of hooks around a little bit more on this side than you see on this side. And so the idea here is that this side of the disk is actually a little bit closer to the star, and so it gets a little bit more light. And this could be due to a planet on an eccentric orbit that's really forcing the disk to be off-center. And so this is one thing that we're doing with the debris disk survey is trying to search for these morphological signs of planets that we don't have the sensitivity to detect themselves. One of the other things, and I mentioned this a little bit earlier, is we've been trying to understand the composition of these debris disks. And so this is work that was done by Pauline Arriaga out of UCLA. And so here we're again looking at the 4796A disk. Here we're seeing it in total intensity, and you may notice that some of that extra stellar gunk, the residual speckles, have been mostly removed, and that's because we use a technique called angular differential imaging that helps us get rid of it. But you'll see also that the disk looks kind of weird, and you can see these shadow disks behind it as well. And so this technique of ADI, angular differential imaging, actually causes this, we call it self-subtraction of the disk, that changes our perceived morphology. And it's something that we can forward model, and this was a big part of Pauline's work, was forward modeling this disk. So you can see the model here on the right captures a lot of these features. And the other thing that Pauline worked on here was modeling the scattering phase function, both in polarized intensity and total intensity. And you can see that on the right-hand side here in blue. What's labeled here as model, these are the forward modeled scattering phase functions. And one thing that's come out of Pauline's work here is really that our grain models are a little bit behind where our data is. Our data is now outpacing the grain models because we can't simultaneously fit the total intensity and polarized fraction scattering phase functions. You can see the best that we can do right now, at least with simple grain models, are in the red and the green right here. And I think that this points to an interesting position that we're in of really pushing the limits on our understanding of these grains. This is something we've also seen. Bin Ren has a paper using GPI data and HST data, looking at the colors of the disks, a different disk. But he found a similar thing, that right now our grain models are incompatible with the measured colors, and he can't reproduce the disks that we see, or couldn't reproduce his disk just with these simple models. So I think one thing that's exciting about this large collection of data from the GPI debris disk survey is that we really have a lot of data to start to probe these questions in greater detail, searching for hidden perturbers as well as understanding the grain compositions of these disks. So I'm going to switch gears a little bit now and talk about polarization in thermal emission, so getting to the atmospheric characterization side of things. And here I'm going to talk both about directly imaged planets, so thermally emitting, young thermally emitting planets, as well as brown dwarfs, both free-floating brown dwarfs and companions. And here, what happens in the atmospheres is we have a nice orange photosphere here that's emitting unpolarized light. And in the upper layers of the atmosphere, if we have thin hazes or clouds that scatter the light towards the observer, it can pick up this preferred polarization. Now, in the case of a completely uniform atmosphere, we actually get equal amounts of all the different linear polarization states. And so as we observe this object as an unresolved source, which is the case for all of our planets and brown dwarfs, all of this light, essentially, the polarization works to cancel itself out, and we end up with an unresolved source, even though this polarization is occurring within the atmosphere. So to get a polarized signal, we actually need to have some kind of asymmetry in the atmosphere. And so here's an example of a big fat central band of clouds, or clouds in the pole, where we end up having different amounts of polarization coming out of the different parts of the atmosphere. And so in this case, we have the band at the center being more polarizing than the poles. And this can give us with this, this can leave us with this net polarization that we can then measure. So I'm gonna give you an example here of a study where we've actually done this. And so this is a program that I led a few years ago to look at the lumen 16 brown dwarf binary. And for those of you unfamiliar with the system, lumen 16 is actually the third closest system to Earth after Alpha Centauri, Barnard's star. We have this brown dwarf binary pair called lumen 16. And one thing that's nice about it being so close is that we can carry out some really high signal to noise studies. This was a very cool study done with HST of measuring the dynamical masses of these two objects by looking at the absolute and relative astrometry. And so here you can see both the motion of the Earth as it kind of swings in these loops over about a year and a half. But you can also see the planets orbiting around, or the brown dwarfs orbiting each other, getting closer and further apart over time. And this has allowed us to get a very precise dynamical mass measurement on these two objects, where lumen 16A, the more massive component, is about 33 Jupiter masses, and lumen 16B is about 29 Jupiter masses. Now, these objects, in particular lumen 16B, are also variable objects, so brown dwarfs that are showing signs of weather patterns. And we can use advanced techniques, again, taking advantage of how bright and close this object is, such as Doppler imaging. So this is monitoring the line spread function in high resolution spectroscopy. And as bright or dark spots move in and out of view, it dims certain parts of that line spread function. And so you can back out a cloud map, as was done here in 2014. You can also back out cloud spot maps just using photometry, though you can see the models are not quite as high quality. And this was all done for lumen 16B, which is the more variable of these two objects, sometimes seeing variability on the level of 10% peak to valley. In lumen 16A, there's been some work to do this as well, but in general, it's far less variable. And because of that, the rotation period isn't even well constrained. So with these huge kind of variations in the lumen 16 spot map, In 2018, I led a program down at VLT using NACO to try and measure the polarization of A and B, taking advantage of the infrared wavefront sensor to separate the two objects that have an orbital separation on average about 1 arcsecond, using the H-band polarimetry mode. And the idea here was really that we were going to monitor B to try and catch some of these spots moving in and out of view, and that would break the asymmetry that we needed to get a polarization signature. And to our surprise, we found no variability to within our detection limits, but we found that both A and B had rotationally, what's the word I'm looking for? Average polarizations over their rotation periods. And so A had a measured average polarization of 0.03%, and B had a measured polarization of 0.01%. And this is not at all what we expected. Not only did we expect B to have time varying polarization, and it didn't, but we didn't really expect to see anything for A. And so we can then go back and think about different atmospheric scenarios that may cause this kind of polarization. And one of those things is oblateness. So if an object is rotating fast enough, it gets kind of squished down, and that also causes a break in the asymmetry that could give us a polarization measurement. And we explored both of these scenarios for lumen 16A and lumen 16B. And we found that given what we know about the system, lumen 16A, we couldn't explain the measured polarization as being due to oblateness. But in the case of lumen 16B, we could. So without that explanation for A, the only thing left that we could really think of is that this object has bands in the atmosphere that could be causing this. And so we explored a couple scenarios, basically just to show that bands could cause this measurement. And we could find that pretty easily, that a two-banded model could create a 0.03% polarization. And the point here isn't really that we think that this two-band model is the unique solution that would cause it, but it was more showing that it was pretty easy to get that level of polarization once we introduced bands into the atmosphere. We could do the same thing with lumen 16B. So to reproduce the smaller measurement, we could make the bands a little bit smaller. But in this case, it's unclear whether that polarization is due to bands or oblateness. And this is pretty exciting because we now have very good evidence for bands, thanks to our polarimetry measurements in lumen 16. We also know from brown dwarf GCM models that we do expect banding in brown dwarfs. And we even see banding in the thermal emission and obviously in the scattered light as well from Jupiter. Now, admittedly, this isn't the first evidence for bands in brown dwarfs. There's been some really nice work looking at Spitzer photometric phase curves. And there are a number of objects where we see the variability go basically from nothing and then jump up very quickly to peak to valley of 10% variability. And there's been some nice work showing that this could easily be explained if you have 3 different bands that have a brightness that varies sinusoidally over time. And these bands have slightly different periods. And so you end up getting beating in your photometric signal, where sometimes they add destructively and sometimes destructively, sometimes constructively to your photometric signature. And I think in this case, you can also get this little bump there, for example, could be explained by a spot in addition to these bands. One of the main differences here, though, with this polarization work is these bands, the signal that we have for these bands doesn't appear to be variable. This is a constant signal that occurs over the rotation period. And so it's, this technique is now giving us access to a different type of phenomenon within these objects. Or obviously are related to these varying bands, but it really gives us another angle from which we can start to characterize the atmospheres of these objects. And of course, we want to talk about exoplanets. So I've talked a lot about Lumen 16, a brown dwarf binary. And we've started trying to apply this kind of measurement to exoplanets.
Is anybody else not hearing Max?
Yeah, he just cut out.
Oh, we got so close.
So close.
All right. Well, let's give him a moment, see if we can get him back. Max, if you can hear us, either shout or drop us a note in the chat or something.
Yeah, your audio cut out, Max.
Okay. Well, while we're waiting on Max to come back, I'm seeing already some questions come in, which is great. Oh, and now it looks like he's totally gone.
Yeah, he's not in here anymore.
Yeah. Okay. Well, as you're typing questions, and let's just make this people are already doing this, but please indicate who your questions are for in case we have to circle back and do Q&A a little later on. And I'm wondering if we should go ahead and do that now.
I think he's back.
I'm back.
Okay, great.
Yeah, I think I don't know if you saw my last slide. Yeah, I'll just bring it up again. Let's see. Oh yeah, okay, so exoplanets. Okay, y'all can hear me?
Yes.
Great. I'll be very quick. We've started looking at directly imaged planets and brown dwarf companions. We haven't detected any polarization yet in these objects, but I think that there are some next steps we can take. In the coming year or two, we're going to have an upgrade to GPI going to Gemini North, and this will give us a better AO system and coronagraph design, which will help beat down on our limiting noise for our polarimetric measurements. I'm also working on a polarimetry upgrade for NERC2, and this balances GPI a little bit with a bigger field of view, so going for some further out companions. And the pyramid wavefront sensor allows us to access redder targets. And then finally, I guess I've lost the image here. We're working on a project at Palomar called WorkPol that gives us slitless spectropolarimetry in the J and H band, where we're trying to probe more free-floating brown dwarfs. And so I think I'll leave it there since I'm over time and there have been delays, and just take questions from here.
All right, thanks, Max. I've got a couple of questions here. Carl Staplefelt wanted to know, could you tell us a little bit more about the GPI 2.0 upgrade, and especially polarimetry capabilities and what science they will enable?
Yeah, so most of the GPI 2.0 upgrades are going to be to the AO system and coronagraph system. And so where that benefits us for disk science is mainly lowering the speckle noise floor. So in a lot of our observations, most of our observations of debris disks so far were limited by photon noise from the uncorrected speckles. And so as those speckles get pushed down, so do our noise limits for disk imaging. So I think that's going to be the main advantage of GPI 2.0 for disk imaging, which is great.
Okay. Colby, how are we on time? Do we need to move along?
Yeah, you have for one more.
Okay. One more question. This comes from Yayati Chachan, who asks, is Lumen 16A rotating faster than 16B since its bands might be latitudinally thinner? Acknowledging that we know the rotation period may be for only one of the two objects.
Might have lost him again.
I didn't know if that was that or I read the question too fast.
He might be gone.
Yeah. Okay. Well, let's leave that question.